A violent seismic jolt struck one of the world's most important mining corridors late on Monday afternoon in northern Chile, rattling communities, industrial facilities, and transportation networks tied to the global copper trade. The earthquake, measured at magnitude 6.9, erupted beneath the arid landscape near Calama at exactly 21:52 and 20 seconds Coordinated Universal Time on May 25, corresponding to 5:52 and 20 seconds in the afternoon local Chile Standard Time. The tremor originated approximately 29 kilometers, or around 18 miles, east-northeast of Calama, at a depth of 109 kilometers, or nearly 68 miles beneath the surface. Within minutes, the event reignited attention on one of the most seismically dangerous tectonic boundaries on Earth, and the immense industrial infrastructure built directly above it. Questions rapidly spread across Chile's mining heartland after the shaking began. How vulnerable are the massive copper extraction systems operating across the Atacama region to powerful intermediate-depth earthquakes? How much strain continues to accumulate beneath the Andes after more than a century of destructive seismic activity along the South American margin? And how many more major earthquakes are locked within the enormous collision zone where the Nazca Plate disappears beneath the South American continent? The earthquake occurred in a region carrying extraordinary strategic significance for the global economy. Northern Chile hosts some of the largest copper-producing districts on the planet, including extensive open pit mines, mineral processing complexes, water transport systems, electrical infrastructure, and freight corridors connecting the interior desert to Pacific ports hundreds of kilometers away. Calama itself functions as a crucial operational hub for mining activity across the Antofagasta region, an area responsible for a substantial share of Chile's copper exports. Because copper remains essential for electrical grids, renewable energy systems, electric vehicles, telecommunications equipment, industrial machinery, and military manufacturing, seismic activity near the country's mining belt immediately attracts international attention. The quake's depth distinguished it from many of the shallow crustal earthquakes that frequently strike Chile. At approximately 109 kilometers beneath the surface, the rupture occurred within the descending Nazca Plate itself rather than directly along the shallow plate boundary interface. Intermediate-depth earthquakes such as this one form under very different physical conditions compared to shallow megathrust events. Instead of representing direct slippage between tectonic plates near the surface, these deeper earthquakes develop within the oceanic slab as it bends, compresses, fractures, and deforms while sinking into the mantle beneath South America. That immense geological process has shaped the western edge of the continent for millions of years. The South American arc stretches for more than 7,000 kilometers, or roughly 4,350 miles, from southern Chile northward toward Panama. Along nearly the entire margin, the dense oceanic crust of the Nazca Plate moves eastward and descends beneath the lighter continental crust of South America. The convergence rate varies depending on location, ranging from approximately 65 millimeters, or about 2.5 inches, per year in the northern sectors to nearly 80 millimeters, or more than 3 inches, annually farther south. Those measurements may appear small when viewed over a single year, yet over decades and centuries the accumulated tectonic pressure becomes enormous. The result is continuous deformation of the continent, uplift of the Andes Mountains, volcanic activity, and repeated generation of powerful earthquakes. Northern Chile sits directly above one of the most active segments of that subduction system. The geological complexity beneath the region is extraordinary. Scientists divide the subducting Nazca Plate into several segments based on the angle at which the slab descends beneath South America. Some portions plunge steeply into the mantle at angles between 25 and 30 degrees. Other sections flatten dramatically and travel nearly horizontally beneath the continent before resuming their downward descent hundreds of kilometers inland. These variations influence volcanic activity, crustal deformation, and earthquake distribution across western South America. Northern Chile lies adjacent to one of the major zones where intermediate-depth earthquakes repeatedly occur within the descending slab itself. Earthquakes in this category typically form between depths of approximately 70 and 300 kilometers, or around 43 to 186 miles beneath the surface. Although generally less likely to produce catastrophic surface rupture compared to shallow megathrust earthquakes, intermediate depth events can still affect enormous geographic areas, because seismic waves travel efficiently through deeper rock structures. Residents across parts of northern Chile reported prolonged shaking as the earthquake's energy propagated outward through the crust. The desert terrain surrounding Calama contains extensive mining installations carved directly into some of the driest land on Earth. Gigantic haul trucks, conveyor systems, crushing facilities, processing plants, and worker accommodations operate continuously in an environment already challenged by extreme temperatures, water scarcity, and rugged topography. Seismic disturbances introduce another layer of operational risk. Chile occupies a unique position in global earthquake history because the country repeatedly experiences some of the strongest seismic events ever recorded. The same subduction system responsible for Monday's earthquake also generated the devastating magnitude 9.5 Valdivia earthquake in 1960, still recognized as the most powerful instrumentally recorded earthquake in modern history. That catastrophe unleashed destructive tsunamis across the Pacific Ocean and permanently altered scientific understanding of megathrust earthquakes. Since 1900, numerous magnitude 8 or larger earthquakes have struck along the South American subduction zone. Many triggered deadly tsunamis and widespread destruction extending far beyond Chile's borders. Although the recent Calama earthquake was considerably smaller than those historic megathrust disasters, it occurred within the same broader tectonic engine continuously reshaping the continent. The location of the earthquake also drew attention because northern Chile has a long record of significant intermediate depth seismic events. One of the best-known examples occurred in 2005, when the magnitude 7.8 Tarapacá earthquake struck farther north within the same tectonic environment. That earthquake demonstrated the ability of deep slab events to generate extensive regional shaking despite occurring far below the surface. The Atacama Desert region surrounding Calama is especially important because of its concentration of mineral wealth. Chile consistently ranks among the world's leading copper producers, and the northern mining districts form the backbone of that industry. Massive deposits extracted from the desert supply global manufacturing chains spanning Asia, Europe, and North America. Even temporary disruptions to Chilean mining operations can influence commodity markets, shipping logistics, and industrial planning worldwide. Copper demand has intensified further during the worldwide expansion of renewable energy technologies and electrification systems. Electric vehicles require significantly larger amounts of copper than traditional internal combustion automobiles. Wind turbines, solar farms, battery storage systems, transmission infrastructure, and data centers all rely heavily on copper components. That dependence has elevated the strategic importance of Chile's mining sector to levels extending far beyond traditional industrial use. Earthquakes present a persistent operational challenge throughout the Chilean mining industry. Modern mining facilities are typically designed with seismic considerations incorporated into engineering standards, yet the scale of infrastructure involved remains immense. Open pit operations can extend several kilometers across and hundreds of meters deep. Tailings storage facilities may contain vast quantities of processed waste material held behind engineered embankments. Pipelines transport water and slurry across remote terrain. Rail systems and highways connect inland facilities with export terminals along the coast. Even moderate structural disruptions can create substantial operational consequences in such environments. Ground shaking may interrupt power systems, damage road surfaces, trigger slope instability, disrupt communications, or require temporary shutdowns for safety inspections. Because mining operations frequently function around the clock with large industrial machinery and explosive materials, seismic response protocols are critical components of operational planning. The earthquake's depth likely reduced the severity of surface destruction compared to what might have occurred during a shallower rupture of similar magnitude. Deep earthquakes generally produce broader but less concentrated surface intensities because energy disperses across larger volumes of crust before reaching populated areas. Nevertheless, intermediate depth events can still generate strong shaking across wide regions, particularly in areas with vulnerable infrastructure or unstable geological conditions. Northern Chile's landscape reflects millions of years of tectonic collision. The Andes Mountains tower above the desert plateau, while volcanic chains stretch along much of the subduction zone. Yet volcanic activity itself varies depending on the geometry of the descending Nazca Plate. Regions where the slab flattens beneath the continent often lack active volcanism because the altered geometry changes mantle melting processes. In contrast, steeper segments commonly coincide with volcanic arcs. The interaction between tectonics and resource formation is deeply interconnected in Chile. Many of the mineral deposits now mined across the Andes originated through geological processes associated with subduction, magmatism, hydrothermal circulation, and crustal deformation over immense timescales. In effect, the same tectonic engine generating destructive earthquakes also created the extraordinary mineral wealth supporting Chile's modern economy. Calama stands near the center of this industrial and geological landscape. Located in the Antofagasta region at high elevation within the Atacama Desert, the city functions as both a mining service center and transportation hub. Workers, equipment, fuel, chemicals, and processed minerals move continuously through the region. The surrounding terrain contains some of the largest open-pit mining operations ever developed. The seismic history of Chile has profoundly influenced national building practices and emergency planning. Repeated exposure to major earthquakes forced the country to adopt some of the strictest seismic engineering standards in the world. Structures throughout Chile are commonly designed with earthquake resilience in mind, especially in urban and industrial zones exposed to frequent tectonic activity. Those standards have often reduced casualties and structural failures during major earthquakes, compared to other regions facing similar hazards. Yet no engineering system can completely eliminate seismic risk. Earthquakes remain inherently unpredictable in timing, and the immense energy involved in large tectonic ruptures can exceed design assumptions. The challenge becomes even greater in remote industrial regions where infrastructure spreads across vast areas of rugged terrain. The Nazca Plate itself plays a central role in nearly every aspect of Western South America's geological evolution. As the oceanic slab descends beneath the continent, pressure and temperature increase dramatically. Portions of the slab release water into the overlying mantle, promoting partial melting and magma formation. Compression shortens and thickens the continental crust, helping elevate the Andes. At the same time, strain accumulates along faults and plate interfaces capable of generating destructive earthquakes. The geometry of the subduction zone beneath Chile is far from uniform. In some areas, the descending slab maintains relatively steep angles into the mantle. In others, particularly beneath portions of central Chile and Peru, the slab flattens into so-called flat slab segments, where volcanic activity becomes absent or significantly reduced. These structural variations influence earthquake patterns across the continent. The recent earthquake near Calama occurred within one of the major clusters of intermediate depth seismicity associated with the bending and deformation of the descending Nazca Plate. Such earthquakes provide important clues regarding the internal stresses affecting the slab as it travels deeper into Earth's interior. Although hidden far below the surface, these processes ultimately shape the seismic hazards facing millions of people across South America. Chile's position along the Pacific Ring of Fire ensures that seismic activity remains a permanent reality. The Ring of Fire encircles much of the Pacific Ocean basin and contains the majority of Earth's active volcanoes and largest earthquakes. Subduction zones dominate this tectonic belt, where oceanic plates descend beneath neighboring plates and generate enormous geological energy. The economic implications of earthquakes in northern Chile extend well beyond immediate damage assessments. Copper markets react closely to disruptions involving Chilean production because of the country's dominant role in global supply chains. Mining companies operating in the region routinely monitor seismic conditions due to the potential impact on extraction schedules, transportation routes, worker safety, and export logistics. Large earthquakes can also influence groundwater systems, slope stability, and rock stress conditions within mining areas. In open pit mines, shaking may destabilize pit walls or trigger localized rockfalls. Underground operations face additional concerns involving tunnel integrity, ventilation systems, and seismic-induced collapses. For this reason, mining regions across Chile maintain extensive monitoring and emergency response systems designed specifically for earthquake hazards. The timing of the earthquake during the late afternoon local working period added further attention because industrial operations and transportation networks remained active across the region. Northern Chile's mining districts support thousands of workers commuting between facilities, processing plants, and urban centers. Industrial schedules frequently operate continuously with rotating shifts extending through day and night. Chile's long relationship with earthquakes has shaped public awareness to an unusual degree. Residents across the country are accustomed to seismic movement, ranging from minor tremors to major earthquakes. Yet even in a nation familiar with tectonic activity, strong earthquakes near critical industrial zones command immediate concern because of the potential economic and infrastructural consequences. The broader tectonic setting behind the Calama earthquake continues evolving constantly beneath Western South America. The Nazca Plate advances eastward every year, carrying oceanic crust toward the continental margin before descending into the mantle. That relentless movement ensures continued deformation, mountain building, volcanism, and seismicity across the Andes region far into the future. Earthquake scientists classify most South American seismic events into several major categories. Shallow crustal earthquakes occur within the overriding continental plate and typically originate at depths up to approximately 50 kilometers or 31 miles. Interplate earthquakes occur directly along the boundary between the Nazca and South American plates, generally between 10 and 60 kilometers or 6 and 37 miles deep. Intermediate depth earthquakes, including the recent Calama event, develop deeper within the subducting slab itself between roughly 70 and 300 kilometers below the surface. Each category behaves differently and poses distinct hazards. Shallow crustal earthquakes may produce intense localized shaking and surface rupture. Megathrust interplate earthquakes can generate enormous tsunamis and regional devastation. Intermediate depth earthquakes often affect wider geographic areas because their seismic waves travel efficiently through deep crustal structures. Northern Chile and southwestern Bolivia represent one of the primary clusters for intermediate depth seismicity along the South American margin. The distribution reflects the geometry and mechanical behavior of the descending slab beneath the region. Many earthquakes concentrate near bends or changes in slab angle where stresses intensify inside the plate. The Atacama region's dry climate adds another dimension to infrastructure management. Extreme aridity limits corrosion in some settings, but creates other engineering challenges related to dust, water transport, and thermal stress. Mining facilities often rely on extensive water delivery systems stretching across large distances from coastal desalination plants or inland aquifers. Earthquake damage affecting such networks could create operational complications extending beyond immediate structural repairs. Transportation corridors remain equally vital. Copper concentrate and refined products move from inland mines toward Pacific export terminals through highways, railways, and pipelines traversing difficult terrain. Even temporary interruptions can create cascading logistical effects across international supply chains. Global attention toward copper production has intensified, alongside the worldwide transition toward electrification and renewable energy. Analysts increasingly describe copper as one of the defining strategic metals of the 21st century because of its role in power transmission and advanced manufacturing. That strategic importance means seismic events near Chilean mining centers now carry implications reaching far beyond South America.